Welcome everybody to today's civil engineering lecture of our Futureproof Your Planet lecture series. This is an online lecture series designed to inspire students, answer big questions around what sustainability look like and why Manchester is the ideal place to come and study and learn about this. The world faces extraordinary environmental challenges, and we, like all universities, have a crucial role to play in meeting this challenge. In our lectures, we'll explore how we can all future-proof our planet and tackle today's sustainability challenges. We'll demonstrate how our world-class research is already making a difference. And we'll help you understand the true Manchester spirit, the one where our researchers are driving change for future generations. By participating today, you've already demonstrated a strong dedication to addressing current challenges. And as a student, perhaps even a future University of Manchester student, your potential to influence a more sustainable world is significant. And just in time is our student and colleague, Chala. Hi, Chala. I've just introduced the series. Just so everyone can know what to do today. So I think the next step is just to introduce yourself and the academic, if that's okay.
Yes, of course. You have introduced the series, right? Yes. So hello, everyone. My name is Chala. I'm currently a third-year civil engineering student at the University of Manchester. I initially got into sustainability because of our overall need for change in our approach to climate change and how fast we need to react to it. And throughout the years, my interest in sustainability has grown, especially sustainable urban development and improving the resilience of cities to climate change. And today, our speaker will be Dr. Mithila Echinta. Dr. Mithila Echinta is a senior lecturer in sustainable infrastructure materials at the University of Manchester. Currently, he is the program director of all civil engineering undergraduate degree programs at the university. Dr. Echinta is a chartered structural engineer, a corporate member of the Institution of Structural Engineers, and a fellow of the Higher Education Academy. Prior to joining the University of Manchester in 2020, Dr. Echinta obtained a PhD in structural engineering from the University of Cambridge, and prior to becoming a university lecturer, he was a postdoctoral research fellow at the University of Oxford. Without further ado, welcome to your lecture towards low carbon construction, sustainable civil engineering.
Okay, thank you, Chala and Nikki. Yeah, I'll start my lecture. This is our future-proof towards a future-proof planet in civil engineering. So I have a specific title. I would say sustainable construction. Sustainable construction. Yeah, I think I don't need to introduce myself. You know, my name is Mithila Echinta. I'm senior lecturer and also a program director. Yeah, before I start my talk, I think probably you already know about Manchester, but probably just to introduce, we are one of the oldest universities in the UK. And next year, 2024, we will celebrate our 200 years of existence. So that's really good. And probably you know Manchester, it's northwest of England, quite famous for football and various other reasons. University of Manchester is birthplace for many science and engineering discoveries. So when you learn your physics, probably you heard about these names relating to electrons, nuclear physics, quantum theory, etc. And more recently, graphene. Graphene was invented at Manchester early 2000s. Yep, and also there are other famous discoveries or famous people, fluid dynamics. Probably you heard about Reynolds number when you do fluid, and then Alan Turing in terms of computing, etc. It's a quite nice place, and also we are one of the largest universities in the UK, over 40,000 students, and also we are quite, we are ranked quite up in world ranking. This is one of the QS world ranking, one of the most well-known world ranking system. We are number 32 at this year. So all sounds good. Okay, just an introduction about the university. Yeah, in my talk, I first introduced civil engineering a little bit, and then sustainability challenges. I first introduced the challenges in terms of sustainability, why we need to consider them, and then possible solution. I mean, that's what we expect from students. So you are the people in 3 or 4 years' time take these challenges. So I will provide you some insight into our latest research and how we are dealing with solving this sustainability issue, or make sure our planet is sustainable. And with my program director hat, so towards the end of this talk, I will provide a little more information regarding our undergraduate programs. Okay. Yeah. So what is civil engineering? I mean, civil engineering is everything we see built around us, and we can tell it's built environment. So roads, buildings, bridges, public places, hospitals, offices, and also water supply, power supply, and everything. And usually we think these are granted, but actually these things will not exist unless the greatest effort of civil engineers. For example, water supply. So in the morning when you wake up, so you need to go to a washroom, so you need water. But if water is not there, obviously there will be a big trouble. And same thing with roads, I mean, if we can't go to our workplace or university, that's where civil engineers made our life better. Okay? So it can be buildings, as I said, road networks. This is a tunnel construction, I mean, for rail infrastructure, and then water dams and various stuff. And not only new construction or new structures, this is like a protection, coastal protection, again, really important. So civil engineers are the ones who would save the world. I mean, we have a major role. I will go through the details later as well. And then water supply and also wastewater treatment, etc. Okay. However, I mean, if you do not have any family background or no one in your family who could explain more details about what civil engineers do, what we do these days, normally you type on Google. And this is what I got when I search on Google and I search images. And these are the ones I got on first few pages. You can always see that civil engineers, I mean, like someone wearing a hard hat and having a drawing or a surveying equipment and supervising a construction project. So probably, as far as I'm concerned, this gives a wrong picture. I mean, civil engineers are not just supervising a construction project. Civil engineers do a lot more. This is one of the job, but it's not all. Okay, civil engineers do more interesting work. So what civil engineers do? I mean, we are the one who design, who create, manage, everything. Residential, commercial building, transport system, even those traffic signaling systems, water supply, sanitation, energy generation. So I'm aware that now our civil engineers increasingly work in renewable energy like nuclear power plants, offshore power plants. So it's very, very wide and very diverse. Okay. Yeah, in short, we are not just supervising construction projects. So what we do, we are the one design, create, and connect the world around us. Okay, good. Okay, now move into the challenges. I think this is probably the main part of the talk in terms of sustainable development goals. So I believe some of you, if not all, are familiar with these sustainable development goals set by the United Nations. Actually, civil engineers have a very key role in achieving these sustainable development goal. If you can see here, number 11, which sustainable cities and communities, which is where exactly civil engineers has the major role. And then climate action. So we need to protect our planet against various climate action, global warming, sea level rise, everything. Life below water, life on land, and on the top you can see no poverty. Again, it's really important. I mean, for example, agriculture, civil engineers are the one who supply or create these water supply systems. And then zero hunger, good health, well-being, even buildings. If you are living in a building, it's really important we have good health and well-being. So those are really important, quality assurance. And then number 5, on the top of right-hand side, you can see gender equality. So we would like to see more and more female students and students from very diverse background who have a part in our civil engineering community. So I think there are 17 sustainable development goals, and out of number 16 here, peace and justice, strong institution. Other than number 16, as far as I am concerned, civil engineers have a role in all 16 sustainable development goals. So that's the thing you need to do. So when you practice as civil engineers, so these are the things you must ensure. For example, number 11, I would highlight it again, sustainable cities and communities. Okay, then what are the problems? What are the problems? Why civil engineering is not sustainable? Okay, so why we need to protect our construction industry, for example. So one reason is unsustainable demand for materials. I think you are from various parts of the world, and probably you can see construction sites everywhere. Okay, for example, in Manchester, I can see so many construction sites. So which means we need a lot of materials. And probably I mean, these materials made from natural materials. For example, glass is made from sand, type of sand. Then cement is made from, again, like calcium carbonate sources, clay, and then concrete, we need sand, aggregate, again, all natural sources. So we have unsustainable demand for materials, especially some part of the world, China, India, I think there's a construction boom. So which means they need more and more materials. And that's one issue, that's a sustainability issue. And also we have a carbon issue, which means the production, production of these materials, for example, cement, glass, steel. I mean, you need a lot of heat, I mean, these are fabricated or manufactured by heating various raw materials. So a lot of carbon emissions, and you need a lot of energy. So the materials have a high carbon impact. And another main issue, I will again discuss this in details, something we call linear use of the materials. Okay, I'll come into that in my few minutes time. So these are the main challenges. So for example, unsustainable demand for materials, and the materials are very high carbon impact, and linear use of the materials. So in next few slides, I will go through these in detail. Okay, probably you can see these numbers here. So how much materials used in construction industry all over the world? For example, 4 billion tons of cement, 10 billion tons of concrete, imagine. Do you know in the world population, which means about around 8 billion people at the moment. So which means on average, one person use more than 1 ton of concrete. I mean, it's a huge amount of material. Actually, concrete is the most widely used human-made material, and it's the only second to water. I mean, water is not a human-made material, so that amount of material, and then other material like steel, glass, aluminium, timber. So we need a lot of materials. Okay, so that's a problem. And as I said previously, most of these materials, construction material like cement, glass, are manufactured using raw materials, so raw natural materials. On this graph, you can see this gray color thing, which is the effect of construction minerals. I mean the natural materials we need to produce construction materials. So which is nearly 40% of all materials. I mean, out of all materials we used in our world, more than 40% is due to construction related. So you can see how significant the influence is. For example, I mean, in 2011, I mean, they estimate or they calculated that people use 35,000 million tons of raw materials. Okay, these are the raw materials, as I said, sand, clay, calcium carbonate sources, etc. So that's that much. And if we continue, this trend, because more and more infrastructure, more and more projects, so probably they estimated in 2060 If we continue, we might need 80,000 million tons of natural materials. The problem here, our demand is increasing, but the supply will not increase. We won't get more and more aggregate, or we won't get more and more sand, so clay, etc. So, materials will not grow that fast, at a faster rate, compared to the demand increases. So that's the problem. So that's why I'm saying, at the moment, our construction industry is not sustainable, because demand increases at a rate higher than what the nature can supply. Okay, so we definitely need something to do here. So which means reduce the demand. Okay, so we must reduce the demand. So which means we have to be clever. We can't continue how people used to build things 60 years ago. Because 60 years ago, people did not consider these things in greater details because materials were available. But now, unfortunately, we can't do that. So that's the sustainability issue. Okay, that's the sustainability issue. The second one, I'm going to talk about the carbon impact. So, and this pie chart, you can see the two brownish color regions. One is building operation, and the other one is building materials and construction. See, if you add those two, it's 39. So I simply make it 40. Okay, I said about 40. So about 40% global carbon emissions are due to buildings, okay, or construction. So it's 40% is due to construction, materials and operation. It's really important, building operation, because we need lights, we need heating, and we need ventilation. So we need a lot of energy. We use a lot of energy to run or function our buildings, okay, which include in residential buildings as well as commercial buildings, or hospitals, schools, everything. So it's a 40% is a huge, significant influence. And even here, for example, transportation shows 22%. Some of these transportations are due to construction related emissions, because you need to transport materials from manufacturers to construction sites. So, and then construction need heavy machinery, okay, cranes, trucks, all these things. So a lot of fuel are consumed. So huge impact, okay. And then in terms of materials, and you can see on this bottom right-hand chart here, I highlight, for example, cement, 7%. Out of entire carbon emissions due to various industries and various products, 7% is alone, 7% alone, 7% comes from cement alone. Okay, it's quite significant. Okay, cement manufacturing. So definitely we need to reduce the demand for cement and reduce the demand for concrete, for example. Okay, so that's the carbon challenge. So I said there are three challenges. One is the sustainability challenge, I explained already. And the second challenge is the carbon challenge. And the third one, I want to highlight linear consumption of the material. So what that means, we usually extract materials. I said we use raw materials, natural materials like sand, clay to make construction materials. And then we make what we want, like glass, cement, okay? And then we construct our structures, buildings, etc. So what happened after the use of the building? I'm pretty sure you have seen this type of places wherever you live. You just dump construction waste into, or a landfill or a site where you can dump these things. So we are not closing this loop. What we need is circular economy. Circular economy, we need to close this loop. At the moment, it's linear. So we need to close the loop. So which means we need to either reuse or recycle. So then that's again really important when we construct structures or when we design structures, we need to think about end of life. We can't just throw the concrete or steel into a landfill because it's not sustainable, obviously. Okay, good. Okay, I don't want to go through these details. Okay, then the solution. Okay, so those are the problems. And what are the solutions? So these solutions are based on some of the research carried out, research areas I am involved with. For example, I'm very interested in low carbon and sustainable construction. Okay, how we make our material, our constructions contribute to a less carbon footprint, and also our structures or constructions are sustainable. Obviously, what we can do, I think I will discuss based on my 3 previous key areas, previously identified 3 areas. Unsustainable demand for materials. So that's the first issue I discuss. How we can solve. So we need to be very careful, or we need to be innovative. We can use less material. So if we use less material, if you remember that slide, I mentioned 4 billion tons of cement, 10 billion tons of concrete. Can we make it less? Less amount per year. Not only one country. So I'm not focusing on the UK or wherever you are. I mean, it's not just UK. We need to make sure we apply these things all over the world. So we need to use less material, and we need to use material efficiently. We need to use materials more efficiently, and we need to make sure these materials have better technical and durability performance. So which means they are stronger, better, and last long. So you need less maintenance. So if we can do that way, so if we use less material and we use materials in a better way, efficient way, then obviously we can reduce the demand for materials, raw materials. If you remember the numbers on my previous slide, I said if we do not do anything, we might need 80,000 million tons of raw materials per year in 2060. So that's not sustainable, because world can't produce or provide that amount of material. So that's why we need to use less material. And then high carbon impact. So I mentioned, for example, cement is very carbon intensive. The production of cement or the use of cement is really carbon intensive. So we need to use better materials, low carbon cement or low carbon concrete, for example. Then I already mentioned about circular economy. I mean, which means either reuse, recycle material. So we need to think these at the construction stage, or at the design stage. You can't think about recycling or reusing once everything done, because there is no opportunity to do that. So you need to think this from the very beginning. Okay. For example, I said concrete and cement are the one of the most significant in terms of carbon impact. For example, because as I mentioned previously, you can see concrete is everywhere, every structure. It's a wonderful material. It's really good material. It's a simple material, and also durable. Anyone can make it. Everywhere you can do it. But the carbon impact is really, really high because of the volume, and also we less reuse or recycling. Okay, those are the 2 reasons. So what we can do, I think probably this diagram is clear. This shows if you take a meter cube of concrete, how much carbon in there based on different materials. Don't worry about the other things. Those are small quantities. This green one, okay, sorry, blue one. So the blue one on the top, that's cement. So more than 80% of carbon in concrete is due to cement. So which means we need to reduce the amount of cement, or there are other materials we can use. Especially, I mean, I do a lot of research on this area, a number of waste materials, so byproducts from other industries have cementitious characteristics. So we need to study these in detail, their chemistry, because, structures we need to design for 100 years, it's not just for 1 year, 2 years. So definitely, so we need to think, we need to do a lot of serious research how we could use alternative cementitious materials. So if you could, as I said here, this light blue area, which is 80% of the total carbon impact come from cement. So if you reduce the amount of cement, obviously we can make concrete less carbon or cement less carbon. Okay, clear? And then we can think about new materials. Probably you come across this material called fiber reinforced polymer, FRP or CFRP, carbon fiber reinforced polymer, used in other industries, aerospace, automobile industries, because they are superior strength, lightweight, they are durable. So probably we can think about more advanced materials. So we can use advanced materials, new materials, advanced materials to make sure our structures are sustainable and low carbon. Okay. So those are material carbon. If you remember, I said building operation or running buildings. I mean, if when we live in a building, we need heating, lighting, all these things. So that consume a lot of energy as well, which means have a high carbon footprint. Can we think about reducing the operational energy, operational carbon? So we can make buildings more energy efficient. So one way of doing this, glass, if you compare, I think probably you have seen modern buildings, modern buildings, they use a lot of glass compared to all the buildings, either brick work, concrete, rather than, or steel. I mean, especially these facade, non-structural areas. I mean, we can use a lot of glass because glass makes sure buildings, I mean, we can use daylight, and also we can use solar heating system, even solar panels, so that we can generate energy from solar light, So, I mean, we can use glass, I mean, nowadays, actually, I mean, probably you have seen this, a lot of glass, buildings, modern buildings have a lot of glass. That's fantastic. But however, glass is, it's a brittle material, brittle mean when they fail, they shatters into small pieces, And also, usually glass is the most fragile part of a building. And this is from a real structural damage or structural failure. And you can see glass windows all fallen, whereas the other structure, main structure, remain intact. So, and this can cause serious, injuries to people. And this is something I have seen in Manchester. This is vandalism, unfortunately. Again, this is a bus stop. I mean, this is a photo I took while I was walking. Yeah, I mean, it's completely shattered. So this is vandalism. So glass fail like this. It's not like steel or concrete. Okay. So, but however, the use of glass is fantastic. As I said, that can improve the energy efficiency of the building. Okay, that can enhance the energy efficiency of the building. So, however, that's a low strength, brittle. Brittle means they shatters into small pieces. So what we develop, type of laminated glass. So because we can't change glass, okay, because transparency, I mean, the key factor of glass is transparency. But however, we combine with, this is a picture showing experimental result, and you can see this glass beam or panel is bent. I think probably you never seen in real life glass bent like this, they shatters. So we develop some new interlayer material, so where we make glass is stronger. Okay, glass is more stronger, so which means we can use in real life application. So that's something. And this is even after it failed, you can see the glass pieces are still intact, or it's still in the same place. It's not like fallen apart. If you remember the previous picture I have shown with that bus stop where everything is shattered, but here still intact. So this is after failed. So that's really good. That sort of research we do. Again, I don't have all the time to show all these things, but I want to highlight one more key thing. At the moment, when it's come to, this is again a challenge when you start as civil engineers. At the moment, when it's come to construction projects, there are key parameters. We think about cost, obviously, because either it's a government project or an individual project or a company project. Cost is really important. So cost is one criteria. And then also we need to make sure structural viability. Structural viability means they are strong and they are durable. Okay, unlike other things like cars, mobile phones, computers, we don't want to use 100 years. Okay, but buildings or structures or infrastructure project, bridges, I mean, we want them to last more than 100 years. So it's really important. These are durable. So we in traditional or at the moment, designs are based on cost, structural viability, and durability. We don't want structures to collapse. But I think in near future, very soon, the designers must consider carbon consideration. So not only cost, structural viability, and durability, carbon is also important, the carbon impact. So that's why I mentioned all those previous, my research, where carbon, I mean, low carbon is a key. For example, we need to think about carbon impact for the whole life. It's not just material. I mean, this is a stat. Don't worry too much about the detail. For example, we need to think about the whole life cycle. Whole life cycle means the material stage, construction stage, use stage, demolition stage, and life after current life, I mean, reuse, recycle. So when you do a design, I think probably 5-10 years time, I'm pretty sure you need to consider whole life performance, not just the current structural performance or cost performance, whole life carbon impact. So that's really important. I think these are the things I think we try to make sure that we include these things into our curriculum, where we teach students about the sustainability and carbon management, etc. Okay. Good. Okay, just to summarize, so how to make, I think I already mentioned challenges. So what are the simple things we could do? I mean, what you need to do as civil engineers. So we need to improve our material efficiency. So we need to use better materials in better ways. Okay. And avoid over design. So we no need to, over design our structures. And then number 3 is that circular economy, which means we try to reuse or extend the lifetime of structures, and use of low carbon materials. I mentioned about low carbon cement, low carbon concrete, and we need durable materials, things like fiber reinforced polymer. And then also, as I said, think about this one also important when it's come to carbon. I mean, if we can use local materials, so that's really helpful, because otherwise you have to import materials from like maybe countries which are 4,000 miles or 5,000 miles away. So that will not help, even though materials may be low carbon, but you need to consider transportation. That's why I said that whole life. So whole life consideration is really important, not just the material. Okay, good. And this is one example I did. I can't provide much details because a consultancy project I did for major infrastructure project in the UK. And I mean, at the moment, so this project is at their early stages, and the gray color one was their original plan. I mean, the carbon footprint due to their original design. But now, with our consultancy or our advisors, so they managed to reduce the colorful one is the real the current one, and they are about 30% less carbon. So 30% less carbon. Okay. And they want to keep improve. Okay, and if you think, I mean, can we make this low carbon alone? Probably it's not going to work. So we need to make sure the cost as well. So for example, at the moment, construction industry has an economy about 8 trillion US dollars. It's huge. So for example, if we use less material, obviously that help because material cost will down. Okay. And also when we use less material, structures become less heavier. So probably we don't need heavy machinery. Okay, type of things. And I mentioned about local supply. That's really important because if you use local materials, then transportation cost, everything. So as far as I'm concerned, all these low carbon things are really important, but we need to think about the cost as well, because if we do not consider cost implication, probably we will struggle, or you will struggle to ensure people or the society accept these solutions. So, I mean, cost is really important as well. Okay, that's about my the main lecture. But since, as I said, since I'm the program director of civil engineering programs, I have few slides just to mention. I mean, yeah, I mean, we are part of a School of Engineering. This is a new building we have here. We call it Manchester Engineering Building A and B. And then, so what you do, I mean, so I know you are very good with maths and physics, perhaps, so that's why you are interested in engineering. What we will make sure, I mean, at the university, you need to develop these skills, solving real life problems, because it's not like solving a mathematical problems. You are already very good with solving mathematical problems. So real life problems, I mentioned those challenges, and designing, analyzing, calculating, and being creative. And finally, what you are doing, you are applying science and maths to real life problems. Okay, so that's sort of a thing you will do. And then we have, I mean, if you're on a 4-year program, so you're learning about probably 60 course units. but we have like 4 core themes. One is structures, materials, hydraulics, and geotechnics. So in every year, you learn some course units within those areas. And with recently, we actually, myself including, because I joined the university about 3 years ago, where I included a lot of things on carbon calculation, sustainability type of things into our curriculum. So that's what you learn. So 4 main core themes: structures, materials, geotechnic, hydraulics, and then project management, and then sustainability. And then in addition, you will learn team working, some practical skills, etc. Okay, I don't want to go through this one. Yeah, I mean, we have different type of teaching. For example, specialized technical units, I mean, like, as I said, material structures, climate change, fire engineering towards the end of your course. And we have other things like individual project, group projects, research project, design projects, yeah, various type of projects. And then where you can practice things like teamwork, etc. And communication. Communication skills are really important for engineers. Okay. And yeah, okay. Then and then we have some field course. This is in year 2, and all students like this one. 2 around a week field course in Easter time, or just before, I mean, springtime, where you do this surveying field course and part of a design course unit as well. So that's non-traditional. Okay, it's not just lectures, not just lectures. You have various activities. As I said, field course, lab classes, projects, research projects, design projects, individual projects, group projects, etc. And there are a lot of things you can do at the university, and also Manchester is a big city, and you can have a lot of fun as well. Yeah. Okay. Yeah, finally, I mean, civil engineering industry is very wide, very, very wide. So you can do various jobs. You can be a structural engineer, geotechnical engineer, transportation engineer, energy engineer, environmental engineer, construction manager later. Probably you can't be a manager just when you pass out, but I mean, when you graduate, but I mean, probably a few years later. And finally, if you are like me, if you like to study and research more, probably you can become an academic as well. And we really enjoy our life as an academic because we want to inspire a future generation, which what I am doing right now as well. Yeah, with that, I want to stop. Thank you very much. And also there's a pledge page. I think you can probably, I think you have been told about this, I believe, or otherwise Charla will mention it. Yeah, with that, I'm happy to stop. Thank you very much for listening. I think that, we can have a Q&A session, I believe.
Yes, okay, then we have a couple of questions. I'll just start with one. So I think there's an attendee wondering if there is any overlap between civil engineering and architecture, and what are the key differences, as they have interest in both, I think. So they're trying to decide between which one they want to choose.
Unfortunately, as for now, we do not have combined course units with civil engineering and architecture. So we have civil engineering, but within civil engineering, we have specialized areas. For example, in 4th year, you can specialize on structural engineering, or we have industry placement. I mean, if you would like, I mean, for example, if you're very keen on architecture, I mean, you can join with our civil engineering program with industry placement option, where after 2nd year or 3rd year, you can enroll with like a 1-year industry placement. So, I mean, that could be an option.
Yes.
Yeah.
And I think what they were asking is kind of what is the difference, I think, in general roles of their.
Okay. Yeah, I mean, when it's come to civil structural engineering, so it's more engineering side, isn't it? I mean, architects is more like the physical, visual side. I mean, it's about, for example, things like occupants satisfactory. For example, I mean, as structural engineers or civil engineers, probably we are not that. We do not have that expertise in things like that, people satisfaction, whereas architects are the ones who are very keen on things like, people satisfaction at the building, etc.
Following on, someone has asked, could we use biodegradable materials with similar properties to cement or concrete?
Okay, that's a very good question, and we are research on those as well. Yeah, it's possible. One of the key thing we need to consider, I mean, in the UK and perhaps other countries as well, um, I mean, for example, all the buildings, for example, need an insurance, need an insurance. So, I mean, because unless the client take the risk, we need to make sure, somewhere the building is insured. So when you go to like insure a building, so the things they ask about the material, for example, brickworks, like a regular construction or standard materials, there won't be an issue. Yeah, that's a very good thing, and that's what we try to do as academics. Not myself alone. I mean, we have a number of academics, and we have a number of forums. For example, Green Building Construction Council. So what we need to do, Charla, thing is like we need to include these into like policies. Policies, and so that the design codes. Probably design codes, because in practice, in real life application, the structural consultancy firms, they do their design based on design codes. So what we try to do, even with, probably you heard about graphene concrete, for example, and other concrete types with GGBS, fly ash, etc. I think one step we must do, we should include these into material codes, design codes,
right.
and then standard testing. Because again, for example, steel, say, deformed bars. So if you test in the UK, China, India, it's the same procedure, and you can specify the strength. But in terms of this type of new materials, we need specific and strong specifications. Otherwise, someone do it differently. Because that's why I said, even in my presentation, when I mentioned about low carbon cement, and we need to be extremely we need to have very good understanding about their chemical side. We don't build a structure for 1 year and demolish it. No. So we expect them to be 100 years long. So yes, the answer is yes, possible. A lot of work going on. Yeah, definitely. Maybe 20, I don't know, maybe 10 years time, we would see more material. For example, at the moment, codes allows using recycle aggregate, recycle aggregate. So I think they allows up to 30% of recycle aggregate. So that's in code. Now in the UK, any concrete supplier, they use recycle aggregate there in concrete. So in future, I expect these things are also regulated, and then people can use it.
Yes, actually, going off of that recycled aggregate point, someone has a similar example about they're asking you what you think of using recycled plastic in the aggregate in construction of roads nowadays.
Yes, when it's come to straw, I think it's a good question. When it's come to concrete and other materials, I mentioned when I mentioned glass, actually. So we have structural materials and non-structural materials. For example, load-bearing members and non-load-bearing members. I think we can try even with those the previous one, like new type of cement and concrete. There is if a building structure, for example, slabs, floor slabs are not the critical. They don't take a lot of loads. So there's a possibility that we can try these things in non-structural application first, because if again, end of the day, what we need to reduce the demand for virgin materials, and then somehow minimize the use of high carbon intensive materials like cement. Okay, so yeah, there are various non-structural application. Even when it's come to tunnel, I involved with some industry project. They have various what you call temporary construction. Okay, temporary mean not like just 1 day and remove it. So probably they will last there for like temporary road for 2 years or 1 year until the project completed. Obviously, we don't need to use high usual cement or concrete for those temporary constructions. So obviously we can use this type of new materials or as I said, a non-standard material. Yeah, non-standard materials in those type of applications.
Okay, great. Thank you for that. And I think we have a question about carbon emissions and carbon offsetting is what I'm understanding from this question. But if we have interpreted your question wrong, please can the attendee clarify? So they've asked if it would be more or less cost effective to reduce the cost of carbon emissions, which from what I'm understanding is the government's policies on having a certain cost to emitting a certain amount of carbon dioxide?
I haven't got it, to be honest. So would you mind repeating it, Chala?
Yes. So would it be more or less cost effective to reduce cost of carbon emissions? I think they're trying to ask about
Like
how
offsetting, like you give money to different projects where
exactly. I think offsetting is what they mean. Yeah.
that's an option as well, that's an option as well. But I think in terms of real civil engineering or real structural engineering, I would like to consider, as I mentioned, that whole life consideration. For example, if we build a building, and if we make it like modular construction, like rather than one single thing, if we have like modular structure, so once we want to change the building or we think this building is no longer usable, we can, dismantle it and use in somewhere else. I think we need to consider that sort of a whole life consideration where like modular construction is really good. Another application is 3D printing, again, type of 3D printing application where we can use materials more efficiently. As I said, in construction industry, material wastages are quite high. It's quite high as 40%. Okay, so we think about things like fabricate offsite, which means at a company we produce these panels and then you transport to the construction site and make it. Again, there are other things you need to consider. Distance, the access constraints and all these things. But if we can do that, because when you make, say, some panels at a company, they make maybe thousands, they can use the same formwork, same mixers and high quality. And that's obviously way efficient than someone make their panels at a construction site. We could do that type of things. Again, we can consider, or we can include the effect due to transportation, because obviously the transportation then includes some carbon. If you consider whole life carbon consideration, then we can decide, how low carbon the real solution is. I think modular construction, offsite construction, those are really needed, and we need to consider about this, because after service life, say 60 years, rather than demolish it and throw into a landfill, I think we need to use it. Recycle aggregate is fine, Chala, but the problem is recycle aggregate. Again, you need a lot of energy. You need to crush it, small amount. So,
transportation again.
recycle, to me, I would simply say recycling aggregate is not recycling material. It's more like downgrading. So we downgrade the use. What I really want, actually I have a project. So we can use those beam segments or slab segments as it is in a new project, rather than you crushed again and take the aggregate only.
Oh yes, that sounds interesting. That sounds like a good idea to work on.
And the other thing I think probably the student asked, there are options, probably you donate some money to a project where they plant trees in somewhere.
But actually,
yeah. That's actually possible, and that's going on as well. Yeah.
Yes, I think though, this attendee might like to, if you look at recent EU rules and regulations are actually, they're banning placing ads saying that a product is, you know how when you buy something, it sometimes says that it is carbon neutral because the company has done carbon offsetting. The EU is actually banning it because it's actually found that it's not as effective, or it's not carbon neutral, so.
I think that process alone may not be sustainable, isn't it?
Yes.
Okay, that's fine. You can make a contribution. The celebrities do that as well. They use private jets and then they donate money to some charities or
exactly
to offset their carbon impact. So, as a real civil engineer, I prefer, we do something engineering to save the planet.
Yes, I agree. We have another question. This is more course related, but for a student interested in green buildings and coming up with sustainable solutions to environmental problems, would you recommend a degree in civil engineering or joint civil and environmental engineering?
Environmental engineering is very wide, isn't it? It consider, for example, land use, isn't it? Some universities, they have this environmental engineering on for example, land use. and or water. I mean, so some universities, I mean, their environmental course units, I mean, they probably consider more on water. I think my advice is probably, I mean, they go to the details, because normally most, even our university, I believe other universities do as well. You can check the course unit structure, and you can see what are the course units available. Again, I mean, I don't know how students think nowadays, but I mean, probably, I mean, you can specialize things probably at a little later stage of your program. For example, our programs, I mean, first 3 years are basically the same. But in fourth year, if you want to specialize on structural engineering, we have structural engineering. For example, I'm the course lead for a course unit called structural engineering design. And then we have colleagues who do fire engineering or earthquake. Okay, that sort of specialization. To answer that question, my thing is probably better you go through the details of the program and what they exactly mean, environmental engineering. Because to me, environmental engineering is a very wide area. People might address things like climate change, I mean, the model, for example, we do things here, I mean, things on climate change, I mean, type
Yes,
of
we do
work.
a lot of modules even just for civil engineering.
Yep,
I'm
yep,
quite happy with our
yep,
course.
yep.
Yeah. There's a question about 3D printing that you mentioned earlier. They're asking, do you think that will be a significant method in the coming years? And is it a sustainable material while being durable enough? So does it satisfy the strength requirements for a building, and is it sustainable basically?
Okay, good question. Someone probably more interested in structural side. I think as for now, I mean, suitable for some application, but for example, it might not be good for like a road bridge, heavy structure. But as I mentioned, like temporary type structures, like say exhibition. So if you need a space, or if you need some space for like a some building for like a exhibition, then you can use that modular construction I mentioned. So you don't need to print one at sites. You have those pieces and you bring it and then construct it, and then you remove it after 2 years or 3 years, or sorry, 2 months or 2 weeks. Or maybe things like temporary, things like due to a climate thing like a flooding or a war, unfortunately. I mean, if you need to provide temporary shelter for people at a short notice, and that's again a solution. Yeah, I mean, some application, as far as my knowledge, okay, I think I'm a chartered structural engineer as well, so probably I should know this. I mean, I know this. I mean, as I said, I mean, 3D printed concrete for like a road bridge, road bridge. No, the technology is not that advanced, but some cases we can use it. And then the other part is the materials. Yes, I mean, actually, I have 2 PhD students working on that. I mean, again, we try to use alternative materials with less cement. Otherwise, 3D printing at the moment, they use more cement than even regular concrete, because I mean, the paste or the binder, we call it binder material, they don't have the aggregate. Aggregate means large rocks, etc. I mean, so which means you had to put more cement. So we are working on like some natural clay materials, so they need. That's why I said, I mean, depend on the application, Charlie, because for example, it's a very tall building, say 30-story building, but the ground floor column, so you might need very strong material there. So I mean, depending on the application, that's why, I mean, we don't have, that's why you student learn all these fundamentals, material behavior, structural analysis, structural design concept, environmental consideration in geotechnics, although I don't have much expertise in geotechnic area. And we need to find a solution suitable for that problem. We can't take a solution which works in one site to somewhere else. Probably that solution might not work because the ground condition can be completely different.
Yes, of course.
Yeah, I think that's why really important. I mean, nowadays, and probably some student might think whether university course is the real is really required, because nowadays you can learn things from various sources, online sources, etc. But I think these basic fundamentals, I mean, you still need the understanding, how materials behave, how structures behave,
especially to be an engineer. Yes,
yeah,
definitely.
how ground behave, for example, and then earthquake. I think probably I think early this year, unfortunately, there was incidents in Turkey, a serious earthquakes. I mean, unfortunately, I think what I read. I mean, again, that's not my expertise area, but I think it seems, although, for example, some countries we have the technology, we know the knowledge, but unfortunately, those buildings were not designed
They were
considering
not up
earthquake.
to standard, actually, is what happens in those.
That's what happened. That's really important, That's why I say probably a solution work in somewhere, Manchester might not work elsewhere.
As well, of course.
Yeah.
We have a question, and they're asking if you could recap on how to convert linear use of materials into more of a circular model, for the use of materials.
Okay, again, very interesting question and something I'm very interested in as well. I think that's why I said we need to consider this whole life from the design stage at the very concept. I mean, even at the design stage, the early stage called conceptual stage. So you need to think about the whole life. I think my advice is, or that's what I do as well. I mean, I consider whole life consideration at the very beginning. Otherwise, what you need to do, what you can do, the options are very limited. Either recycle, aggregate, okay, not bad, but I'm saying it's not fully use of circular economy, or you just need to throw them. No, I think definitely you need to think about from the very beginning. As I said, that modular construction is really important. And think about the material, probably, child, I mean, concrete is very good in compression, whereas weak in tension. For example, if you have a system where concrete can be completely in compression, and then you have a tendon, something like external tendon, which provide the tension. And then later, when you want to dismantle it, you remove the cable or you cut the cable, and you can take the concrete pieces separately. I think we need that sort of thinking from the very beginning of the design. Otherwise, I think the options are very limited.
Okay, great. Thank you. And one final question. How can collaboration between scientists, engineers, environmental scientists, and policymakers drive progress towards sustainable solutions?
That's really good question, and that's what we do. For example, I mean, I have background in materials as well as structural engineering, but I'm not expert on materials. So, for example, chemistry, for example, cement, and definitely we are working with, for example, with the people who has the materials background, material characterization, and chemical side, chemistry, obviously. And then some students ask about architects. We need to collaborate with architects as well, because they are the ones who know, people's expectation, what would make buildings more energy efficient. Although I mentioned that use of glass, okay, that's from structural engineer point of view, but the architects are the one who knows best about in terms of how to make buildings energy efficient. So we need to work with architects. And policy, I already mentioned things like put this into design codes or government policies, Green Building Council, Green Construction Board, and design codes, because we need these things under regulation and policy. And the final thing I mentioned, that carbon calculation. At the moment, companies, they do it like a voluntary basis. Okay.
Yes.
I mean, it's not a compulsory requirement as for now in the UK for structural design consultancies to consider carbon into design. I think probably this will happen in future. I really want this to be happen.
Yes,
Probably
hopefully.
carbon quantification is an essential. That's again a policy. I think that's really important. That should be a government policy. And then I mentioned about insuring, because because I bought a house a few years ago, and I know, I mean, to get a mortgage, I mean, in the UK at least, I mean, they ask, the construction materials. So if we have a non-traditional materials, probably you won't be able to get a mortgage. Okay, so therefore, this should go into policy. It's really important. I mean, we need governments, what do you call, support to implement these things, because I mean, recent weeks, unfortunately, there were missed messages. But I think still UK is committed to net zero by 2050, hopefully. That's really a real challenge. And also I'm aware there's a new code called Net Zero Building Code will be in use in future, probably 2030, I don't know, maybe much earlier. So we won't, that's one part of our net zero overall policy. buildings are net zero. So, I mean, I think those things are working. For example, professional institution like Institution of Structural Engineers, Institute of Civil Engineers, I mean, they are working tirelessly to make sure these things are in place. And actually, I'm on the boards or on committees, you know.
Okay.
For example, I structure, I'm in a couple of committees. I'm in the research panel as well. Yeah, we work with the professional bodies. It's really important. And academics, I mean, I think it's really important to be involved with these professional bodies. It's not you just teach based on
Yes, of
what
course.
you learned 30 years ago. I think it's really difficult. Especially, I mean, Manchester, like university, we are a research led, I mean, research based, research intensive university. So everyone use research interest into teaching. For example, myself, I probably remember last year, materials one, I introduced those low carbon concrete type things into curriculum, materials curriculum. And year 4, I introduced this embodied carbon calculation into our structural engineering design project. So students do the carbon calculation now. They are quite familiar. The last year, they won a very prestigious award from the Concrete Center, the sustainability prize for their project.
Okay, that's
I'm
great.
the course lead, so I'm very proud of it. And I'm the person who introduced those carbon calculations into.
Yeah, I think that's one of the really nice things about University of Manchester. We have so many lecturers that are on the boards of committees that determine and kind of measure and look at the regulations in the UK, what we need to be doing and planning the future. So they can, during our lectures, they can look at a certain research and kind of go, this is where the industry is currently heading. This is what we will be doing. This is what we want to do, which is, yeah, amazing to be able to see in your day-to-day life.
Yeah. So that's, I mean, advantage being part of a research-led or research-intensive university. For example, I'm only teaching materials and structural design type course unit. I don't think my head of the department will ever ask me to teach geotechnical engineering or project management. So, I mean, we have people who are expertise. For example, there are people who are expertise on earthquake engineering, people expert on fire engineering. So those are the ones who teach those course units. So that's really advantage. Because our job, only half is teaching, half is research. I mean, there are a few colleagues who are probably teaching for only very few, but more, I mean, majority, maybe 95% of colleagues, they both do research and teaching.
Thank you, Dr. Achinta, and thank you everyone for asking your questions. Sorry that we didn't have time to get to all of your questions, but thank you for attending. Hope you've enjoyed.